And in some cases where we see that SMO2 goes up and stays stable, and then we go and look what the breathing is doing, we see that they're breathing completely hypocapnic. Their breathing is so bad that their end tidal CO2 is about 22, 25. That means their oxygen dissociation curve, the stickiness of their body, shifts to the left side when you use a number. In simple terms, what that means, due to the fact that their end tidal CO2 is that low, they have absolutely no problem in the lungs to pick up the oxygen and put it on the blood. But they have a heck of a problem to take this oxygen from the blood and actually move it into the cell structure to be used. So when we have the question, is it a mitochondrial problem or is it a respiratory problem? When we measure the end tidal CO2 and we see, well, it's a respiratory problem, then we just try during the test to force the guy to get at least normocapnic, if not possible, hypercapnic. And we can change that very easy, and we can show that there. Can you start that one here?
Yeah, sure.
And I will show you that it's very interesting how you can show that on yourself with sometimes very easy tricks that we are actually able to shift voluntarily the oxygen dissociation curve from the left to the right side or not. That means we can change voluntarily arteriovenous oxygen difference. The problem with the heart is with the heart, I have a problem to tell, I like to beat faster and stronger and better. I mean, the performance will basically force you to do one or the other. But respiration is semi-controlled. You can a little bit control your breathing. You can make the decision whether you like to breathe deeper or slower, faster or shallower. You can localize the breathing situation. So it's not completely out of our control. It is completely out of our control when we go all out. But when we actually go with speed, when the breathing doesn't get pushed to the limit, we can make some clear decisions. How and where do I like to breathe? The question is, does that make does that has a difference? So what we have here for the moment, we have, can you start the two Moxys? Just push the buttons, see whether it works. So we have two Moxys mounted here. Okay, that one works, push the other one, so we are working here. And she pushes the other, so that works as well. So what I like to do now is, can you get rid of the workout there, just start the machine. Yeah, you can turn it to watch the cable. Just go on the start.
On the top there, the arrow play button, whatever.
Just turn it to the other button. Yeah, just go there and start. Yeah.
There you go.
Yeah, there you go. One free drink for less. So now what we have here is we have two Moxys mounted. I don't tell too much yet where. It really doesn't matter. So we have her heart rate here. We have her oxygenation on one measured part, and we have her oxygenation on the other measured part, and we have her total hemoglobin on 2 parts. Okay? So when we do a test, we do exactly what Frank is doing with his Fisher flow. When we start the test, whatever test we do, 1 minute, nothing. Just to balance it out. Sometimes we need 2 minutes, nothing. It depends how nervous the guy is. And you start to talk, you can make it really very nervous, and it goes all over the place. So sometimes I have to leave the room, otherwise he gets nuts. Which a lot of people get anyway. So now put one arm up, Marianne. So she has one arm up. We may see, perhaps, or realize which one. Here you have now the graph. This is your trend of your SMO2. This is your total hemoglobin. And this is one. So which number, the 36 or the 72, is the arm which is up? You can't lose. It's like 649. In the worst case, you try a bit. Which one is the arm which is up? Is it the upper one? Or is it the lower one? Just let's wait a little bit. You remember the first reaction? The immediate reaction, the stress reaction. Just look at the number, look at oxygenation, and look at the total hemoglobin. Who is for that? This is the arm which is up.
Good morning.
Who is for that one here? We're about 50-50. So how can we figure it out when we don't know? Well, just put the arm down again. Which one do you think it was?
It's the right arm.
Which one?
72 is the
Yeah,
right arm. Yeah.
71, 2, huh? Just go up again, let's see what's happening. Now watch carefully, sometimes we have to look. You can see despite the fact she's doing nothing, she's doing something. It's a counterbalance. It's not so that guy is doing nothing, he's just doing not as much. And so you can see again how SMO2 goes down, and it's an initial alarm phase. What do you think? Oh, why it happens? And then she starts to balance out. Where you can see it better is not on the SMO2, or where you can see it better. This is a stress reaction because motions in SMO2 also can be influenced by respiration. When she goes up, she will do a breath. No? When you go up with your arm. So you see it much better sometimes in the stability of the total blood volume. That arm, this doesn't move at all, so we don't have an influence of gravity. So we have potentially much less change in total blood volume than we have on the other side. It's not that extreme like would expect, no. The shocking part really is when we're looking at, in physio, somebody has some pain on the arm, you say, well, just keep it up and it helps. We're not anymore that sure whether that is true. The only thing we know, he puts his arm up. In some people, when we do that, we can see, whoa, if he goes with the arm up, the total hemoglobin completely disappears. And it's in mostly very poorly trained people. They have very little muscle tension. So they go up and down. Gravity is the main influence of change of blood volume. If you have people with a decent amount of muscle tension, the blood pressure potentially gets controlled over whole much more than gravity, potentially over systemic vascular resistance and other reactions. So a very, very interesting pace. Now we just wait a little bit what's happened. So what happens here now, it gets a little bit lower than before, but not too much. So what we do now, we just wait. Just let her wait a little. I mean, that arm can't be that happy. You remember when you were in school and you really knew the answer the teacher would ask you? And that stupid guy never would ask me. The only time I could go up with the arm is when I was sure I could give an answer. Every time I didn't have an answer, he would ask me for the answer. And finally, when I actually was keen to give it, I couldn't. No? That's when I realized if I would have a NIRS at that time, I could at least make a study instead of thinking, why I not can finally give an answer. I never give the answer right. Now I could give it. We just wait a little bit. So we will see, actually, interestingly, there is a kind of a pattern here. But you can see the blood volume is pretty stable. Watch here, there is a change now. No? There's a change that we have a little bit an increase in total hemoglobin. But it's fairly up and down. When we look at the difference, it's actually interesting. Is it really the same? No, we don't have the exact same place. It's just the right and left arm. We not can say, oh, that's great, now they're equal. They're not equal. We look at that as a trend, and we look at that as a trend, and we not can argue now, okay, you have to buy this one arm up because then you're equal. Okay, so now what I like is that you start to breathe very, very, very fast. In and out. Deeper and faster. Come on, deeper. Come on. You can do more. What happens? What happens? It goes up. What do you see? Come on, you're not dizzy yet. And stop. Please normal. Put your arm down. What happened in both arms? It goes up. SMO2 goes up. What does that mean?
Delivery jumps.
Her CO2 dramatically dropped. You know, her end-tidal CO2 was potentially clearly below 25. No? Potentially down by 20.